So, as Mr. Heady mentioned, I'm going to talk about structural tie rods today. And just to be quite clear at the very start, I'm talking about solid steel tie rods as opposed to cables. So I'm not talking anything to do with cables today. It's all solid steel. As Anker Schroeder, we only deal with solid round bar. We don't deal with cables. That's a very much more a different niche product we're not into. Yep. So my name is Colin Jacobs. Obviously, I'm based in the UK. I'm also joined by my colleagues Ralph Rummerman and Axel Hagemann. They're based in Germany. We are a German company, and all our fabrication is in Germany. And also, I'm joined by our partner in India, Upkar Raut from Bolin Ventures. So Upkar helps us with recently entering the Indian market, and Upkar's helping us achieve that goal and providing local assistance to any projects we do. So I'm aiming to talk about 50 minutes, with plenty of time for questions afterwards. I can see all your microphones are muted already. That's great. Questions, please use the chat function. Upkar will monitor the chat, and we'll answer those questions at the end. So saves you forgetting any questions during the presentation. Make a note of the slide number, and we can always go back to that. I'm happy to issue a PDF copy of the presentation afterwards. Just please contact myself or Upkar afterwards, and we can do that. So today's content, a bit of a background to Anker Schroeder, talk about what the primary components are we're talking about, what uses we have for structural tie rods, then some design code information, part of the Indian code, but mainly being a European company, we're more specialist in the Euro code. Some common causes of failure we see with tie rods and how we can help you guys as engineers design out these some of these causes and to mitigate any risks you may have. We've got a brief example of quite a famous failure in the field. Now I'll go through some project examples. So a bit of background to Anker Schroeder. Again, we're a specialized company based specializing in solid steel tie rods. We're still family owned, relatively small company. We're only 100 plus employees. But that's big enough to satisfy most of the global demand for tie rods that we see, and 85% of our product is actually exported from Germany. Rather uniquely, we use the forging process, which is fairly unique amongst most tie bar manufacturers, and also we can produce very long single bars, so we can actually produce a single tie bar up to 27 meters in one length. Obviously, with couplers and turnbuckles, we can make that any length we wish, but we can actually do single length bars up to 27 meters. And we're involved with all aspects of tie rod design and use, whether it's ground structures or above ground structures. And 3 of our employees, including myself, sit on Eurocode development committees. So we also contribute back to the whole design aspects and development of the whole construction industry in general. So we deal in 3 main areas, really, with our products. Our first thing we do, we started out life is forging shackles. Our main product area is tie bars for port and marine structures, but we're going to talk mainly about bridges and structures. But I'm going to give you just a bit of background to some of the shackles. So here's a forged shackle. So we take the round steel, we'll heat it, we will press the ends to whatever shape we wish, in this case an eye for the end of the shackle, and then bend it into a bow. And we can make these taller than a person, and generally used in the offshore industry, literally for holding oil rigs to the seabed. And some of the load capacities of these, safe weight for lifting, 1,500 tons is not uncommon. And again, that's a safety factor of 5 upon it. So we work with many of the major petrochem companies. So all these companies use our shackles. We don't sell direct, we sell via distributors. So you will not see our name on these shackles, but nonetheless, we do manufacture a lot of those shackles. As you can imagine, working for petrochemical companies, the approval standards are quite high and the offshore standards are quite high. So we have lots of approvals, all for forging and for our manufacture. But using the same process, we can also make very long tie rods with forged ends. These are generally for the ground containing structures, typically for ports and harbours. Here you can see these 160 millimeter diameter bars with ends forged to make a pin connection, and these bars are actually 18 meters long. So we were able to make an 18-meter long bar in a single piece and ship it to wherever we want to in the world. Now, these are generally used for these types of structures. So this is some land reclamation for a port in Felixstowe. So here you can see the existing land profile. Sheet piles are driven in the sea. They're then dredged material is then pumped into the almost like a cofferdam, if you like. But once you have this soil inside, we then need to tie the front wall to the rear wall. So here's our tie rod being installed. So it goes from the front wall along down to the rear wall. So we basically anchor back the front wall. And this sort of project is where the majority of our tonnage goes. As you can imagine, there's far more tons go in a project like this than a general steel arch bridge. But nonetheless, the bridge work is just as important to us. So basically our tie rods are used in two types of structures. They're the above ground structures, as in the bridges, and ground retaining structures, such as ports and harbours. So typically for sheet pile or even concrete diaphragm walls, we will use tie rods here. Although the tie rod may look very similar, the different types of products have different requirements. If we're doing ground retaining structures, they generally have to be very robust. Imagine you have lots of soil placed on top of this and maybe even a plant driving across them. We have generic type connections which are modified to suit each project because each project is slightly different. We have to allow articulation for the settlement of the fill. Long lengths are good and logistics are a big part of this project, but safety critical. We're looking at above ground structures. We develop a number of standard connections which makes much quicker lead times and allows fabrication of the host structure to be a lot easier. But again, pin connections, very important for length adjustment and stressing facility in this type of tie bar. And again, fatigue consideration, as you guys will be well aware, is a big consideration. And again, also safety critical. And on top of all that, for above ground structures, we have to be also aesthetically pleasing. So the architect generally has a view that he likes these tie bars to also look nice and pretty. So mainly we talk about structural tie rods in this presentation. As a typical use here for a building in a facade, you can see the cross bracing on a project in Scandinavia. Our standard range of bars that we have, we go from M12 to M160. We typically do two grades of steel, a 350 type mild steel and a higher strength 540. Currently we have the largest range of bars in Europe, and we can take load capacities up to 960 tons. And we're also one of the first, or the first company to gain the European technical approval, which means we have an independent body come into our works every year and investigate our production and test our materials to make sure we can use the CE mark in Europe, which is a legal requirement in Europe. So just a few pictures and shots of our casting to show we spent a lot of time doing FE analysis and putting material where it's needed, but also to get a nice flow to the product. So we get a nice seamless flow from the solid bar right up into the pin connection. So this also provides an attractive product as well as structurally sound products. And we can also supply carbon steel or stainless steel. Generally, if it's carbon steel, it will need protecting, so they can be either painted or hot dip galvanized in the main finishes. Stainless steel, generally up to M56, is all that's economically viable. You can do bigger in stainless, but generally the cost is prohibitive. I'll just show some of the typical uses of our tie rods. So facades, we have a building here in London. You can see that all our tie rods here are bracing these transfer trusses across here. And we have a project here with an issue where they couldn't put any piles into the bottom of the ground, some air rights issues, so they just cantilevered this floor out here, and a single bar takes a load back to the roof. We do lots of stadia, so this is a fairly big football club in the UK, but not in terms of the Premier League. Wolverhampton Wanderers. You've probably all heard of Manchester City. So it may appear to you that all these are cables on this structure, but actually they're solid tie rods. So we supplied all these tie rods here to the new stand on the north side. And then one of the most famous probably stadiums in the world, Wembley Stadium. So we supplied over 800 tie rods to the roof structure around here. These are actually cables from the arch, but there's lots of tie rods within this roof structure just here. But today I'm going to talk mainly about bridges. So again, we use the same tie bars as we use for buildings. For bridges, typically steel arch bridges is what we supply for. So traditionally, bridges with an arch would have lots of cross bracing and maybe welded fabrications, but by using something like a similar as a tension bar, you can perhaps gain a more elegant structure, such as this, whether it's a tied arch, network arch, or a cantilever type bridge. These allow for very quick installation and assembly and less site work. So a typical bridge here, cantilever bridge in London, you can see, again, you may think these are cables. They're actually solid bar. It was more economical to make these from our solid bar than a cable, and much quicker lead time. Simple footbridge. Again, this time we use stainless steel, nicely highly polished stainless steel, which the architect required. Again, we have tie rods here for a passenger covered transfer bridge in Dublin. And sometimes, really, it's the style of a bridge. It has to fit in with its surroundings. So here you can see all our tie rods on this bridge next to a fairly old arch, masonry arch bridge in France. We do lots of road bridges, as you'd expect. There's one in Ireland, one in London. Again, these allow just elegant structures to be built, and this, I think, quite nicely fits in with its environment and blends in very nicely. So talking now a bit more about the technical aspects of tie rods. So just looking at the component parts, all very simple. I'm sure you're well aware of this, but simply put, we have a bar with threads on the end. We have the clevis, we have the pin, which attaches to the structure. Often a thread cover is supplied, which has two parts. It makes a nice seamless transition between the fork and the bar, but also provides protection to the thread. We also have, we want to extend to whatever length, we can use coupler or turnbuckles. This also allows in situ length adjustment, and also importantly, if we have a turnbuckle, allows in situ stressing. So once we installed the bar, we can then put any load we wish within the bar capacity into the structure. And importantly, that all components are designed to exceed the load capacity of the bar, as you'd really expect. Now, looking at tie rod design information sources, forgive me, we're still learning about the Indian design codes, but from what we can see, the main ones are IRC 24, IS 800, and maybe the IRS to do with steel road bridges. We're more au fait with the European design codes, as you expect, but what we see is a lot of similarity between the Indian and the European ones, albeit that the European, as probably you gets frustrated as I do, that you don't just need one design code, you probably need about 20 just to read one. So, but these are the main design codes that you can refer to for tie rods, and I will go in a bit more detail about these. Other standards, there's the old British BS 5400, which is still used by some people, but is now superseded by the Euro codes. And we also do some work in America, so we have some knowledge about the USA codes, whether it's AASHTO or the AISC. But typically, we mainly focus on the Euro codes. If we look at some aspects of the Indian code, the IRC 24, says they refer to IS 800, the General Steel Design Code, and also make reference to the Euro codes. So you do obviously have your own design codes, but they play heavily on the Euro codes. It seems I recognise many parts within it, and also 5400. I still recognise some parts from the old 5400. For the Euro code, if we're looking at cables and tension members, on steel bridges, EC3 Part 2, it's a part for steel bridges, and this refers you to EN 1993-111, which is design of steel structures, and again, design of structures with tension components. So this is where the main aspects of tension components will come from. And generally, with solid bar, they come under Group A, solid rod. So again, if you want, you're probably well aware that you can also get wire and strand design detail from this code, but we're generally dealing with just a solid rod. Locally in India, I think generally the main steel you have available in round bar format is generally up to about 350, 490 in yield and maybe up to 60 mil diameter. So for higher grades, you typically will be looking to source elsewhere for that material. But one thing I did note in the IS 800 is your elongation requirements for steel seem to be a bit higher than what the Eurocode states, so 20% in this case for a 450 grade steel. If we look at the Eurocodes, again, part 111 tells us to look back to EN 1993 part 1. So we go to 93 part 1 and these are much common steels, you'll know, from S235 up to S460. So they're the common steels. If you want higher strength steels, currently you then go pointed to part 12, which then goes up to 690 grade steel. Yeah? Now, typically you find, because of the way that steel is manufactured, you don't want to do quench and tempered type steel all the time because it's expensive. You will stick to normalized steel. So you're in around the 500 to 540 grade of steel. It's a more economic to use. You can go higher strengths, but then you'll get into heat treated steel and that increases the cost. So one thing to note also between the Eurocodes and the Indian codes, if you're less than 460 or below, your elongation should be as minimum 15%. If you're using the higher strength, they allow you to go down to 10%. So basically, the higher strength you've got, the less ductility you're going to have. So it's just one thing to be aware if you're looking at Eurocode material. If we look at design resistance calculation, looking at IS 800 gives us the tension member calculation. Again, very simple calculation. Again, you'd all be well aware of this. But one thing to note difference from the Eurocodes is that when you're calculating the area of a thread, they use the root area of the thread and not the stress area as the Eurocodes do. That can make quite a bit of difference to your calculation, so you should be aware of that. Again, if we look at IRC 24, it's the same check. You have a yield check based on the gross section and the yield value of the material. You have a rupture check, again, based on the root area of the thread, the ultimate stress of the material, and again, the partial factor. Another thing to note with difference between Indian and Eurocode is your partial factor for material is 1.1 in India, whereas the Eurocodes use 1.0. Yeah? So when we go look at in closer detail at the Eurocodes, again, we're going back to part 111, which again then points us again to part 18. But again, it's the same kind of check. We check on the yield on the gross section, and we check on the rupture on the thread section. But in this case, the thread section is based on the stress area of the thread, and not on the root area. But if we compare the two, here we have the IRC. So again, we have the gross area of the section, the yield value of the material, the partial factor. This is a minimum of that, and 0.9 times the root diameter, root area, sorry, and the ultimate stress and the material factor for rupture. Again, the Eurocode, very similar. So basically they are the same equations, some different nomenclature, but the main difference being is your calculation of the thread stress area. Yep. Your partial factors are different. You have 1.1 for yield on the Indian codes, and Eurocode is 1.0. Important to note that the difference in the thread stress areas means that the Indian use of root area will always be less than the stress area. Yeah? And if you calculate this out on a typical bar, a typical like M76 bar, you will find there's 11% difference in the calculation of strength between the Eurocode and the Indian codes. So it's just something to bear in mind if you're looking at different systems. The Eurocode also states that you should really look at a loss of one tension component. So you should design for assuming one tension component is lost and take that into case in an accidental design case. If you're looking at connections, I couldn't find much detailed information in the Indian codes, but the Eurocode gives quite detailed guidance as how to connect these. It's a very simple connection, whether you know the thickness of your plate or whether you've got geometry. It gives you standard dimensions you can work to. But however, it is quite conservative. And so we do use sometimes our own methodology on this based on type testing and FEA analysis. Look at pin connections. Again, part 1.8 of the Eurocode gives you some detailed information of how to calculate the capacity of the pin, basically based on spanning across the areas here. Again, this is very conservative. And also, generally in our types of structures, you don't need to consider the pin as being replaceable. That's normally for a different type of structure, so you can really just ignore these bits, and else you'd be too conservative with your pin design. You'll find that if you try to analyze many of the proprietary products out there, you may find that these calculations don't work because they're very conservative, and most people will use their own analysis and type testing to justify. Interestingly, the IRS does give you a bit more leeway for bending, as it allows you to distribute the bearing on the span, which gives you a far better design for the pin. And that's very similar to what the old BS 5400 used to do. So, and we ourselves also use that kind of methodology in our pin design. So with those differences, it's be quite careful how you're using maybe published data, because sometimes you don't know what factors are being assumed within that data, whether they're using partial factor of 1 or what type of stress area they're using. It's the same in our brochure. Obviously, we're a European company, so at the moment we have calculations to Eurocode standards. It's something we're looking to change soon, and then to help engineers in India publish different calculation methods depending on what code they're working to. So typically you just select the load based on what your design load is saying, and it gives you back your diameter. But do be careful that you are using or checking what partial factors have been using and what stress area has been used. So we also offer different lots of data for the fault. This allows you to detail your structure very easily. You can download all CAD files from or Tekla and BoCAD. That gives you all that main information you may need. So we move on to some of the main causes of failure we see in tie rods. So some of the main aspects that we see really can start from design stage. So really the incorrect property are used. Sometimes I think Mr. Hegarty mentioned that sometimes known as PT bar, sometimes these tie rods. You have to be careful if you're using some kind of pre-stressing bar, because often it will not have the ductility that's suitable for use on a tie rod this structure. So be very careful, especially with the high strength bars, that they're always not always suitable because of their robustness and toughness on these structures. So generally if you stick to the normalized steels around about the 500, 540, 460, you're going to have quite a nice robust ductile steel. If you go higher grade, I would suggest you stick to the 690 or below on that and just check its ductility. Misalignment of connections is something we sometimes see, whether that's at design stage or poor fabrication. If your connection steel plate is not in line with the force, then you're putting the tie rod under extra bending. There's poor installation. Quality control on site is very important. Sometimes these tie bars, because of their length, have to be transported in separate lengths and connections made on site. So you do have to ensure that the engagement of thread is correct. Or your fatigue. I guess many of you guys there are experts in fatigue, being mainly involved in bridges. So that's a very important consideration, and often a cause of failure when it's not considered correctly. And then quality control, particularly of some of the components like clevises or cast forks. This can lead to some issues because the quality control may not be as tightly controlled as it is for the bar. So I'll go through some of these in more detail now. So we're looking at misalignment. important when you're looking at typically your welded connections, that your line of force actually goes through the weld detail. You don't want to be putting additional bending on the weld by having incorrect lines of force here. Engagement of thread, so you should always check that there's, the rule of thumb is one diameter at least engaged will generally give you a full strength connection. Again, for the misalignment, typically the tie rod, we allow in our connection design a misalignment of 1/2 degree, but anything more than that, then you'll be putting the plate into bending. Another issue we've seen in the past is pins becoming loose, particularly on, let's say, lighter structures prone to wind vibration, like the footbridges, and you can often get these caps come off. Once the cap comes off, the pin can shake loose under the reversal of load, and that can also be an issue. But looking a bit more at fatigue, now I must say here, I'm no expert on fatigue. I'm sure you guys know far more than I, but this is some of the pointers we do. We do know how to test fatigue and give some pointers as to where to go, but really it's very important for these types of tie rods, particularly on bridges. So here's a typical failure via fatigue. So classic initiation, then back propagation, and obviously we get rupture towards the end. But every project really must need to be considered in its own right. It's very hard for a manufacturer to say, I have tie rods that are fatigue resistant, because it depends on your structure and what your loads are, what your cycles are, what your stress range is. But often we do have test data from other projects where if there's similar kind of stress range and loads, then yes, we can give data as to what the fatigue resistance of the product is. So here we have access to a fatigue test here. So we make a mock-up and we just fatigue it generally to 2 million cycles, and we'll then do a tensile test after that to make sure it still reaches the proof load. By calculation, obviously there's our SN curves, and in the Eurocode they give some detailed explanation of those. Again, I'm no expert on the intricacies of these, I just know the basics of that. But basically for a threaded connection Eurocode, you're looking at a detailed category of 50. But if strictly speaking, if you went to EN 1993-111, the tension member code, they state a detailed category of 105. And if you're testing and your detailed category is 105, that's a very onerous test and very hard to achieve on a threaded tie rod. So our experience is that most engineers will not use this part, and they would stick to just a 1993-19 and detailed category of 50. But the Indian code also suggests its own SN curve. They have a detailed category of 27 for threaded components. So again, it's just another area you should be looking into for the differences there. We have different types of connection types for hangers. Generally, as all the examples I've shown you are threaded connection, because it's very flexible, can be made on site, can be adjusted in length. But we do also have options for forged dies and for welded spade connections. And if we're looking at threads, it's very important if you're specifying a threaded tie rod in a fatigue situation that you specify rolled threads. So a rolled thread has a much greater resistance than a cut thread. So as if you're aware, the two methods of making a thread is generally you can take a steel bar and you can either roll the material, you move material to form the thread, you don't make any cutting, or you cut material away to make the thread. So the two threads we have here, cut threads, you can see the grain of the material here. This is the rolling grain of the steel bar. So here you can see the grain's been interrupted by the cut. Here on a rolled thread, you can see the grain's been moved. This has many advantages. It gives it a much increased fatigue resistance. You get a nice grain flow and increased strength around the root of the thread, which is where often fatigue will fail. But a word of warning, if you subsequently hot dip galvanize a rolled thread, you will severely reduce your fatigue resistance. So again, process control is everything for prevented fatigue failure. We've done quite a lot of studies on thread manufacture and the improvement in fatigue, and what we found is that if you roll a thread, what happens is in the root here, you get a much stronger material, which aids the fatigue resistance. So we found really this is a roll thread before we've actually started loading and after rolling. So you can still see we've got high strength, whereas a cut thread has a very much lower strength in that root. And we conducted also a number of tests where we took cut threads and rolled threads, and we just cycled them up to 5 million cycles. What we found, as we expected, that a cut thread really only got up to about maybe 300, 500,000 cycles before it failed. A rolled thread, we couldn't make the bar fail when a rolled thread after 5 million cycles. But if we galvanized that rolled thread, then again we achieve similar fatigue resistance as having a cut thread. So again, very important, if you're specifying galvanized tie rods with rolled threads, ensure the galvanizing is done before the threads are rolled. Yep. Now your thread won't have any galvanizing protection, so you need to think of another means of how you're going to protect that thread, but do not hot dip galvanize a rolled thread. Another way of eliminating some bending at the connection plates is by use of a spherical pin. So we can provide a spherical seating inside the pin. This allows then up to say 4 degrees of rotation to occur without putting any bending into the system. Because what happens if you don't have that, often it's the bar, the weaker part in bending, that suffers, and this is where the failure will occur. So this can also alleviate fatigue issues in tie rods. I mentioned before that we also have provided forged ends. This is a system common in Germany, particularly for some of the infrastructure projects where they prefer to see a welded detail. And this detail category is actually 140, so very onerous, but we can still make this and get fatigue resistance in exceedance of 2 million cycles. So here you can see we forged the ends of the bar, we flatten out the area, allowing a nice horizontal full penetration weld to 2 sides. So this is much easier than a traditional system used in Germany where they had lots of down welding, maybe 4 welds either side of a tie bar. So now we only have nice horizontal welding and 2 sides. This also allows on-site NDT to be performed a lot easier. So it's a system that may be of interest to you, but obviously the downside is that you do have to have good on-site welding control. And the other major downside really is there's no length control between here. So there's no length adjustment available. You have to be quite precise in your fabrication. Now let's look at one of the most important parts we feel for the structural integrity of tie rods, and that's the quality control, and particularly to do with the castings. Yeah. So many rolling mills can make steel bar very accurately and very high quality. It's rare you get an issue with a rolled steel bar. Issues are always within the connection. Yeah? So how you take that load from the bar to the structure is key. And we say that most tension bars out there on the market, most proprietary systems will use castings. Castings is an excellent process, allows you to perform many shapes economically and at the right strength, but the quality control of that component is critical. We have to ensure that this end transfers the full load, else we don't have a structural system that's robust enough. So in the IRC, they give many castings you can use. I would guess really for structures, you probably use the IS-2644. We don't know much information about that, I'm afraid. What we do know is EN10340. So in the Euro codes, they have a specific casting just for structural use, just for use in structures designed according to EC3. And a typical grade we will use is this G20MN5. So typically it gives us a yield stress of about 300 and an ultimate 500 to 650. But more importantly, it has good elongation at 22% and very good Charpy values. So it's a quench and tempered steel, but this is generally one of the more practical steels to be using for this type of structure. So EN 10340 is quite a comprehensive document. It's very good. It tells you what materials you can select. It gives you weld repairs procedures, which is very important. Although you may think castings come out perfect, often there are defects in a casting that legitimately a foundry can repair by using welding. There's nothing wrong with that, provided you use the correct weld procedure. EN 10340 also talks about factory production control, again, which is a good requirement, and the mechanical testing and what you should expect and what conformance levels there are. However, a big flaw, we think, in this code, it does not specify any NDT. The statement is said that this must be agreed between the foundry and the customer, and the customer in this case will be the product manufacturer. Now, as NDT, it can be relatively expensive. It's often one of the areas a manufacturer will look at to economize on the quality of his casting, or the cost of his casting, I should say. So they have to make certain assumptions that the quality will be met by the minimum NDT. But really, you as a specifying engineer should really look at the NDT and look at it in each project consideration about what the risk of failure is and determine your own NDT requirements for castings, particularly if you're used to Eurocode speak of execution class 4 type structures. Just a brief background to the casting process to explain some of the other issues that can happen. So the casting process, in this case, I'm talking about lost wax, which means how we make the mold out of a wax rather than making a mold out of sand. So we have to, at the same time we make fork castings, also produce test bars. So this test bar here will give me 4 tensile samples. So first we make the mold, we cover the mold, the wax, then we cover the wax in the mold material, we melt the wax out, we pour the steel in, and then we have our raw casting. Now this stage is critical. From here, from a raw casting, it has to go to heat treatment, else you will not get the required properties. Generally at this stage, it may have the strength, but it will not have the ductility. So go into the ovens here, and from the ovens they go into the quench pool. This provides the quenched and tempered properties. Now what's important here is that this test bar is heat treated in these ovens at the same time as your casting, your product. Very important that occurs. With NDT non-destructive test methods, you've got several methods. You've got, for cracks, you can use the MPI test. So we can test the product for cracks. We can test it for internal defects using ultrasonic, or we could even X-ray. Now, all these can be done without destroying the casting. We don't want to destroy the casting, but it does not tell us what the mechanical properties of that casting are. And to do that, we have to do a destructive test. So we have to take our test bar, produce tensile samples, test them. That will then give us our material test cert. So the purpose of this slide really is to highlight to you that when you see a test certificate for a casting, it doesn't represent necessarily a test on this product, it represents this product, the test bar. Yeah? So that's why, going back to my earlier process, that it's very important that that test bar goes through exactly the same production process as the casting. So these are some of the potential problems that can happen with castings. We see sometimes that generally the results you get on the test certificate do not represent the products. They do represent the test bar, but not the products. So really, as engineers, you need to put systems in place that you can check the batch traceability. There should be 1 test bar per melt for castings. Typically for a casting, depending on the size, say an M100 casting, you would get 6 or 7 castings from 1 melt. So therefore, per 6 or 7 castings, you should have 1 test bar result. Checking that the test bar has been heat treated at the same time. Has the product been weld repaired? On some structures, you would need to know that and make sure it's the correct procedure. If you're ever in doubt on a project, really just order for a destructive test on an actual casting from the production batch. This will tell you whether you met the requirements. X-ray is another good way often looking for internal defects, it won't tell you any mechanical properties, but it will often uncover some issues you can't find by MPI or ultrasonic. In this particular example, you can see we have what's called shrinkage. So this is where the material, the casting hasn't cooled properly. Literally, the material is pulling away from each other, creating shrinkage cracks. And again, you have an inclusion here at level 4, all shown on X-ray. If we cut that casting there, this is the type of defect you would see inside your casting. Quite expensive X-rays, but they do show some, they do highlight very visually any defects you may get. But I should note here that not all defects are unacceptable. It's impossible really to get a casting and not expect some defects. There are some very good codes out there like the ASTMs and stuff and the Eurocode which qualify what these defect levels are, and an experienced radiographer will be able to tell you what level the defects are. But typically anything to less than 3 or below is an acceptable defect, an acceptable risk for a casting. So we're going to quickly look at an example of a failure we've seen in the past. I think it was 2008. So this is a bridge that was constructed in the UK, and in about 2008, suddenly overnight, one of the tendons, the tension members here, snapped. The bridge had no traffic on it. It was at night. Luckily, no one was injured, and so it was unusual as to why this happened. What was found in the end was that the casting actually met the yield properties. So they did some, as you can imagine, they cut some samples from the casting. They found it met yield properties, but the charpy and elongation and ductility failed to meet specification. It's almost though the casting had not been heat treated. Yet the foundry had issued test certificates to say the casting met mechanical properties because these were based on the test bars. There was no control over whether the castings went through the same process as the test bars. So really the conclusion of this investigation was that the test bar was not heat treated with the casting. So whilst it maintained the strength, after a few years of being loaded, it basically just failed in a brittle fracture. It does also demonstrate this project the importance of redundancy, because this structure had been designed well. Even though one tie bar failed, it did not lead to a catastrophic collapse, but also it allowed replacement of all the tie rods. So as you can imagine, none of the castings were trusted on this bridge, so every single tie rod was replaced. And that could happen because you could take one tie bar out at a time and just replace it with a new tie rod. Another failure we've seen in the field is a stainless steel casting failure. This is quite unusual, where the product was investigated and it was found to meet all properties, met full specification, absolutely nothing wrong with it, even down to the microstructure of the steel looks good. And so the only thing we could attribute this failure to was hydrogen embrittlement. So often the supplier in this case had polished a fork using an electrochemical process. He didn't achieve the desired result first time, so he put it through again. Again, it's a hydrogen-based process. This introduced more hydrogen, so it's thought that's what led to this brittle failure through the casting. So again, it's very important to realize that your post-processing type things can often have a catastrophic failure effect on some of these castings. In the UK, and I also believe in the US, there's the organization called CROSS. So this is a useful source of information for any kind of failures that have occurred in structures. You may be aware of this. Again, the cases I've talked about are all available through CROSS, so you can refer to that. But also, there are alternatives to castings. We also supply forged eyes. Again, this structure here may look like a cable stayed structure, but actually it's using solid bar with forged eyes. Again, we can just forge a plate and forge a pin here. So the project I showed you earlier in Ireland uses forged eyes rather than castings. Then it comes down to the last aspect of quality, and again, most important is the fabrication control. Luckily, in Europe, we have EN 1090, which controls all steel fabrication, all aspects of fabrication, right down to what the hardness profile of a hole should be, what dimension tolerances you're allowed. So it's a very good document. I recommend you look at this, and there's no reason why you couldn't use it for any of your structures, even if you are designing to Indian codes. In the Europe, we have to supply items CE marked, and to get CE marked, we have to have a European technical assessment. Again, this involves independent checkers and inspectors coming to our plant at least once a year to test our product and make sure we follow the right approvals and material testing. So it can be a very useful document if you're doing some complex structures. And there's also some model specifications which may help you out there. We have our own one. It's a generic one. It may have ASU at the top, but it's a generic giving you the best practices in specifying tie rods. But also, if you want an independent and very comprehensive guide, you can go to the Steel Construction Institute. And they also have a model specification for the purchase of tension assemblies, which again you can find useful. If you need those, you can just contact myself at Anker, and you can assist with those. So I'm going to finish off with just some project examples. So here's a bridge in London, the Overground. So it's like, obviously, it's part of the London railway network. These bridges are M90 tendons, again here. And again, we had to provide fatigue data and do fatigue testing on these to make sure they complied. Interestingly, this bridge was lifted into place in one piece, so it's constructed off-site here, lifted into in one piece. Again, the shackles holding up this bridge are also made by Anker Schroeder via a different supplier. But again, nice view of that bridge there. But again, as you can imagine, safety critical. These trains are running over this bridge maybe 5 or 6 times an hour. So fatigue, very important for these. This is a job supplied to in Spain. This is via our partner VSL in Spain. Again, what I like about these bridges is the elegant nature of these. This is on part of the new Sierra Nevada motorway. And so it's just for relieving really the congestion around the town. Again, we supplied stressing turnbuckles. So each of these tie rods could be preloaded using a special rig. We can also hire out, or some specialist stressing companies also have their own for that. We've done a number of bridges in Belgium over the canals. Again, M85, M100 tie rods. And for this particular test, the engineer was concerned enough about quality to make sure, so he insisted we have independent third-party inspectors, which was no problem. So they came to our works, they looked at the manufacturer, they took away random samples, and they made tests on material. Now this is a bridge very close to our factory, which is great because obviously we made the tie rods, the hangers here. These again, these forged trapezoidal ends. So we supplied 8 of these hangers, 220 diameter, and the ends were forged to a 585mm diameter length, allowing nice horizontal welding both sides and on-site NDT testing. Again, an interesting way of erecting the bridge, made off-site and then lifted into place. Another road bridge, again, you've seen this shot before, the bridge in Northern Ireland, again just showing how the stress is put into the tie rods. So any pre-stress you want to put maybe a pre-camber into the deck can be done quite easily with this type of equipment. The bridge over the Thames, again, allows nice sequential erection of the deck. So you put the hangers in place and just lift the deck pieces into place. Again, stressing can be completed very easily and very quickly on site. Again, Also had to do tensile testing for this project. So this tie rod has already been loaded to 2 million cycles, and then a simple tensile test is performed to make sure it meets the proof load. Now I'm showing this bridge here, but we did not supply. These are definitely cables that are being supplied on this bridge here. But what we did supply is 700 tons of anchorage rods for the mainstay cables, which are split at the ends, individual strands. Then we made a connection that connects to the strands and then go back into the frost blocks at the end. So we had to supply a very ductile steel, high ductility because it's a high seismic area, and that was a successful project for us. Just to finish off now, although this is not a bridge, it's a building, but it's a building inspired by a bridge, which is why I really like this building in London. The problem they had with this building is the underground, you can see the sign there, runs underneath, so no piles were allowed or columns to come down from this face here. Everything had to be in air, so to speak. So this is a design that the engineer came up. You can see the central block and then these two cantilever buildings off here. And this was inspired by, many of you may have heard of the Forth Bridge in Scotland. This is inspired by this bridge. Again, I always like this Victorian shot here, showing the guise of the forces in principle, but the same forces in this building here. So I do like that building. So very architecturally imposing, I think. But again, you see all our tie rods here holding up these trusses here. So just to conclude, in summary, when you're looking at your tie bar systems, we realized, and quite right, there are several standard systems on the market. They all offer similar diameters and load capacity. But some of the key issues you should check really is if they're giving you design resistance, is it using the right factors for your design? Is fatigue an issue? Can test data be provided? Should it be checked? The manufacturer control, it's very important. The manufacturer's control to the correct quality. If you're using EN 1090, is a very handy assessment guide you can use. As an independent check, if it has something like an ETA, that's also a good thing to check. And if Clevis ends are used, just have a warning bell to ask about what the quality regime and what the NDT testing is of that. Just have an open mind to question that. So really, in conclusion, we'd say when you're specifying or looking at your structural tie rods, really use the correct material. Don't have too high a strength, I would say. Definitely don't go over 690 type grade. Don't use like pre-stressing bar type grades. Do your fatigue assessment, certainly if there's dynamic loads. Check alignment of your connections. They go in the line of force. Ensure your specification includes checks for quality control of castings. Specify fabrication standard. And one of our most important points would say is always specify your performance criteria. Don't simply say tie rods by Anker Schroeder M90. Tell the contractor what you expect them to perform to, and then he's got a good chance of making an equal comparison. And I would say if your structure is critical, then insist on production testing, if not full-scale testing on some of the products.
I think as far as that joint is concerned, it is applicable to any joint. Instead of rod, you have another steel also. That detailing category is available. I thought the most critical thing is it's between the fork, clevis and the rod.
Absolutely.
Other than the joint and the rod. Joint and the rod is already available. Detailing categories are available.
Because the joint is still a very standard steel applicable.
Standard steel application.
Correct.
If I can summarize, is this correct? Obviously, we've talked about fatigue here, but what I think Dr. Sabura is talking about is this joint here. Is that what you're talking about?
Yes, because invariably, the joint is very particular to the geometry which we assume for the rod. Inclined, or whether it's used in a tied arch or whatever, that joint becomes a very important aspect.
Isn't that a standard detail in
when we
Eurocodes?
When we get to the joint, so the joint has more or less the highest class, the highest class of notch classes. So you're talking about 140, maybe. I think the biggest one is 165. But compared to that, we are talking about for the rod itself or for the connection and the threaded part. This is more or less the weakest point.
Correct.
Not the fork end, not the fork end, not the tie bar, but still the area around the thread. That means the weakest part is always this this area, and you will see it in every fatigue test and every subsequent brake load test. You have always the failure in the thread area, but don't have any problems with the joint, because the joint is much more higher in its resistance and its calculations compared to the cross section of the tie rod.
That's a drawing of a joint, which is to take the rod eventually, and that's the detail when it sits on top of the bottom boom, on the bottom. Whatever.
Mr. Bobe, here this joint is not particularly, in relationship to the rod which you are using. It is for any structure.
Exactly.
This detailing category is available in the course. I think,
Exactly. Yes.
and only the screw is most weakest point. Rather than this joint, the screw within the clevis as well as the fork is the weakest joint in my opinion. In this particular case, they have already given the detailing category of around 30 or something like that, 30 Newton per millimeter square or something like that. What I can see.